All right, so let's take a look at compression members. So we're going to look at two types of compression members, in particular, solid columns and then bearing walls. Okay, so in wood and masonry, we are going to talk about walls, which we haven't talked about in your basic steel and concrete classes. If you take the advanced concrete, you'll talk about walls in that class. But this is probably for most of you going to be the first experience talking about structural walls. All right, but let's start with columns. So these are going to be direct columns, not as you'd call in steel beam columns with bending and axial. These are going to be axial loading only. Okay. All right, so we'll keep it straightforward here to start out with. In our chapter 3, the general information, they're going to talk about where to find the different types of columns. So in solid wood columns, in other words, not hollow or made out of a bunch of different boards or whatever, you can find information in chapter 3 and section 7. Connector joined columns, built up columns, so other specialty type columns in chapter 15. So columns for wood are, so concrete, there are columns that buckle, if they're called slender columns, but our average concrete column, we don't worry about buckling, right, as much. In steel, buckling is always a big consideration. Wood is going to act more like steel in that respect, so most of these columns are typically what we'd say are long enough that we have to consider buckling. If we have short columns, and that's just a way of implying that it's not buckling, that it's going to be crushing and a strength only. Okay, so when you have something and you're putting it in direct compression, you can, if it doesn't buckle, eventually you'll crush the material or fail the material. If you don't get to that before you buckle, so it can fail by buckling and collapsing, or it can fail by crushing. And you have to, just like in steel, see which one happens first. Okay. So when we're looking at most of these columns, this will be like a board. You've got the parallel to the grain. The load is parallel to the grain. And so in this case, we have compression parallel to the grain. Just like we just talked about with tension, it's a P over A stress. It's just in the compression direction. Okay, so we'll have an axial compressive load P, and we'll have a cross-sectional area A, and that's going to give us our stress. So if we look in the code in 3.6.3, either use the gross area or net area, depending on where the hole is along the length of the member, and the tendency that that member might buckle right at that point where you have a reduced cross section. And at the end of this, I will go through, or at a separate video, but we'll have an example or two on this. If it's braced at the location of the hole, then we can just go ahead and use gross area. So gross area, right, is the full section. But if you've got holes running through, in this case, if we took a cross section, it'd be running through from here to here. I have to get rid of that area when I'm using the net area. But if it's braced at that location, we can still use the grossed area. Because it's a difference between, depending on where the hole is, how likely that is to be an area that is critical to buckling. And also, when I'm looking at if it's not going to buckle and it's pure crushing, that hole makes a little less of an impact because it's only in isolated spots. All right, compression parallel to the grain, which is usually what we're going to see or is what we're going to see for these pure axial columns. We go in and you can look up and see that these are the adjustment factors that we'll be using here. And once again, I'll go in, and now I'm going to go into tables 4A and 4D for sawn lumber, and I'm going to start using some of the different values in there. So we've been using flexure, but now we're going to look at compression parallel to the grain. All adjustment factors are similar to what we used before, except for we now have a column stability factor, C sub P, and the details on that guy are in section 3.7.1. CP is just 1 if it's a supported column that can't buckle, right? It's supported from this braced, as we would call a brace column, braced from the side, or it's a super short column that can't buckle. Several things are going to affect the column's carrying capacity. It's going to be the material, right? Pure crushing or material failure. In condition or in fixivity, right? Same as before. Remember, if we have a pin versus a fixed or a semi-fixed, those things have different buckling patterns, right? You remember that from steel. If you haven't had steel yet, you may have talked about this a little bit in concrete, but I don't, probably in the base course you haven't. So essentially, one of the ways to think about this is if you have a bendable ruler or something flexible that you can use and grab it on both ends and clamp it down like this one, it wants to stay straight at the ends, and so it'll buckle in a shape here. Whereas if these are just pins at the end, so now I'm going to take my finger and push on each side without holding it fixed, and it buckles in this bigger curve. What you'll find is it's going to buckle more easily here than it would here. And so we have different, basically braced links, or I'm sorry, we have different factors that we multiply the length by to get to evaluate the influence of those two, right? Or you could have fixed pinned or something in between. So when you take steel class, you'll get the full, probably most of you have had steel, but you'll get the full discussion on this because it's something we look at quite a bit. So Euler buckling is what I just showed, right? So that's the pure case of a pin. Now we don't actually use pure pin with no fix from rotation in reality. So at the same time, it's not like in steel where we're going to be able to totally weld or fix connections. And so just like in anytime we use buckling, we have that K effective length factor. In our case, we've got basically boards that are framing into other boards or sawn lumber with nails or brackets or what have you. And so then we've got to figure out approximately how fixed is it, right? It's the same problem we have in all modeling of kind of structural connections. All right, the effective length, and this is going to look a lot like any other column buckling discussion you've had. So the effective length, L sub E, is equal to the effective length factor times the length, right? So this is the factor that comes from how fixed the ends are. And where do I find that? I go to Appendix G. It's page 171 in your code. And then we can go through the information on this. So if you want to pull out your code right now, you can go look at Appendix G in page 171. And you will see Appendix G, effective column length, and it's got similar pictures to what you're used to seeing in the steel manual if you've seen those, and what the corresponding effective K values are. Okay, so they can range anywhere from about 0.5 up to 2, and you say, and the pure pin case is K equals 1. So how would I get, which is basically you look at it as I always think of it as one straight curve over the length, right? How could I get more than one? You could have something where, let's just say it's cantilevered, for instance, like this, and I push on it, it's going to do something like this. And so if I completed the curve, that's 2 times. Whereas when I did the fixed, it'd be about a half. Okay, so that's kind of how I look at the buckling modes. So how big a curve or wave that makes, and compare that to the length of the column itself. All right, so if I go into the appendix, in G, we have the different cases, and I don't have a picture of that for you here, but if you go, I would say go ahead and pause and open your code book and look at page 171, and it's got the pictures of the different ones, different buckling modes and end conditions. So there's side sway on 3 of these cases. Okay, so one end of the column can move. So this is a side sway case that I just showed you here. And this is a not side sway. So you see it sways away from the center line here. And 1, 2, and 4, those other 3 cases have side sway prevented, so it's not allowed to move left and right. If there's shear walls that are holding or resisting lateral forces, then you end up with a pretty stiff building, and there's not going to be, you're going to consider that as non-side sway or side sway prevented. If you have moment frames, okay, then there you could have a lot of displacements. What a moment frame just means I have 2 choices, right? If I've got wind or earthquake, I can have a frame that resists that load, right? Just wood pieces. Or I can have a wall that resists that load. The wall is the stiffer option, and that side sway is prevented. If I don't have a wall and I just have individual columns with cross members here as frames, that stiffness and the connections between these two are what are resisting the lateral forces. But I must consider that this is going to have potential for side sway. Okay, so consider side sway. Typically, our wood construction is going to have side sway prevented, and then I can use a K of 1 or less. Now, because wood, basically, if I want to be conservative here, I can refine this if I need to make sure that, like, if I'm close on meeting the requirements. But if I want to be conservative, as long as I have no side sway, I can use K equals 1. In other words, the pin-pin case. Because anything below 1 is going to be more conservative. Okay, so that's nice. We'll just stick with K equals 1 as kind of our first iteration, or if that works, it's fine because it's conservative. All right, column slenderness is the ratio of the length to the radius of the gyration of the member. And you've also seen that. That's your good old in steel, that's your L over R value. So you've got your radius of gyration. If you look in the NDS in Chapter 3, in these 2 sections, you can get that information. For rectangular columns that are solid, I'm going to have to consider both axes. So if I'm looking down on it, it can buckle that way or it can buckle that way, right? These 2 ways or these 2 ways, in and out of plane. Will it buckle more quickly about one compared to the other? Yes, it's going to buckle about its weaker axis. Okay, so I drew kind of a square one here, but if I had a rectangle, it's going to buckle about, let me try this little drawing again since I've made a mess out of it. Let's look at this guy. If this is a sawn lumber, so it's all the same material, basically all parallel to the grain. I have an axis here and an axis here. This is the strong axis because I've got more material farther away, and then this guy is the weak axis bending, right? And it's going to buckle in the weak axis direction. So I'm going to look at the slenderness ratio for both the axes. Okay, this is the depth of the member. This is the effective length. So in the X direction or the Y direction, or whichever way you want to look at Z direction. The maximum slenderness ratio is going to control the buckling capacity of the member. In other words, the bigger of those two, because the depth is going to be smaller, and that's on the bottom. So the bigger one of these two controls. And slenderness ratio must be less than 50, other than in construction. When you're putting it together until you have everything braced in and supported, it may be a little bit more, but after you have completed it and it's all braced in, and then you're going to put in the full loads, then it has to be less than 50. Compression parallel to the grain. If I go into the NDS in Chapter 3 again, I could find this equation. You can also find a version of this equation in the lateral stability appendix, or a version of this. But anyway, this is our compression parallel to the grain, where this value, this guy, is given here. C is 0.8, so little c is 0.8 for sawn lumber, that guy. And my F sub c, and we did this when we were looking at lateral stability, that's why this looks kind of familiar. from that appendix. But 0.8 for solid number F sub C asterisk or star is the reference compression design value parallel to the grain multiplied by all the adjustment factors except for CP. Okay, so you don't have CP yet, so that doesn't get multiplied in there, but that's what this F star C is. And again, we'll do an example for you to look at. All right, so this is the example we're going to do on column capacity, and then we're going to do another one with column design. So I'm going to stop this one, and then we'll switch over to a different video for the example.